So in this example, we're going to complete the square, and the leading coefficient is not a 1. So here you can see I have prepared as a polynomial, and again, it's always going to show up down here. This is our original, so I'm going to write that original in red so we know that that's what we have to have. We're factoring this. So if I add things to my picture, I need to make sure to undo them to maintain equality in my polynomial. So our polynomial, y equals 2x squared plus 12x plus 4. We're going to try to understand why we do this completing the square process and how it looks like on a picture. So what we notice here is if I took all of these things over here, I simply cannot create a square with them. You can go ahead and try. You can also take my word. There's no way to create a square with all of those. So what we normally do when we complete the square is we start by factoring out. We do two things. First of all, that plus 4 at the end, that constant, we just kind of ignore. So like these 4 things, let's just ignore those. But what we start with is we usually say we have to factor out the a term. And then we usually kind of put that little placeholder there. Now what we're doing conceptually with our algebra tiles is, well, instead of trying to create one big square, let's just create 2 of the same exact squares. So what we're seeing here is instead of starting with all 2 x squareds and all 12 x's to try to make a square, let's split them up, right? So what I'm doing here is I'm creating 2 of the same pictures, and each of those pictures should have 1 x squared and 6 x's. So here, I'm going to create 2 pictures, and each of those pictures will have 1 x squared and 6 x's. Remember, these plus 4s are just literally hanging out somewhere. So if I could make them smaller, I would, but unfortunately I can't. So I'm just going to leave these kind of floating in the middle. I'll put them over here. So now what we did then was we focus on this. So in other words, I want to just make one of these things into a square and then just repeat it twice. So we know what that looks like. What we would do is if I want to create a square with 6 x's, I'd have to take those 6 x's and divide them into 2 equal groups, one for the length and one for the width. So that means each of my side lengths should have 3 x's. So in other words, like when we show our math here, we normally take the b value, which is 6, we divide it by 2, and then we get 3. Now, that 3 then conceptually helps us understand that our square will have 3 x's on each side for its length and for its width. Now again, the 2 out front just simply means I'm doing that twice, one for each picture. So that's why I'm also going to do it for this one here. Now, what we noticed then is when I created those length and width, each with 3 x's in them, we created this little square that was 3 by 3. So with our algebra work, normally that means we would have taken that b over 2 and we would have squared it to get 9. And the reason we have 9 is because in the picture that I've created to quote unquote complete the square, right, to make this a square, I'd have to put 9 1s in this picture. So there I've put 9 1s in that picture. But again, I'm doing this twice. So I have to add those 9 1s to this picture as well. But now I have to maintain equality. I've just added plus 9 here and plus 9 here. So if I look down here at my original, this is no longer the original polynomial. If I just simply add 18, it's no longer the same as it was before. So that's why in our algebra work, we usually add like 9 times 2 is 18. We've added 18 to the left-hand side to help balance out the 18 that we've added to the right-hand side. Now in our algebra tiles, we're trying to get factored form alone. So to get that y alone, what we're going to have to do anyway is subtract 18. So that's why on the algebra tiles, if I just go simply add a random 18 of these 1s, I'm going to have to counterbalance it by adding 18 negatives to my picture as well. So now we've completed the square, right? We have this thing here, which is a square. It has a side length of x plus 3 and x plus 3. So that's why we've taken this thing. If we started with 1x squared and 6 x's, we could complete the square into an x plus 3 square. So then our final answer, what we're noticing is 4 and negative 18. Well, of course, that's going to combine to negative 14. What we see in the example is those original 4 1s that we just left hanging out there can now interact with all these negatives that we added to create our squares. We know that a positive will undo a negative. So I'm just undoing some of the positives with the negatives. So what I have left is I have 2 of these squares, right? Here's the first one, and here's the second one. Each of those squares have this dimension. The length is x plus 3, and the width is x plus 3. So we could just write that as x plus 3 squared. Then I should notice that I have negative 14 ones that are not included in the squares. Here I have 9, and here I have 5. So we've completed the square.